Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'll only take you back 25 years. But before I do that, well, you'll be hearing a lot about type systems today and tomorrow, and I wasn't absolutely sure everyone in the room knows what a type system is, so here's my 30-second introduction. So it's based on a cartoon by Luca himself, where he depicts 3 kinds of typing, and his preference is pretty clear. But say you have a language to count fruits, okay? So if it is strongly typed, then 2 apples and 3 plus 3 oranges, that's an error. That's cleanly detected at compile time, preferably. Or if your type system is a little better and has subtyping, it is 5 pieces of fruit, all perfectly sound. If your language is weakly typed, then 2 apples plus 3 oranges, that may be 5 apples, or maybe 42 carrots, or maybe a security hole, okay? And if it is untyped, then there's no apples and no oranges, there's only bits. And 10 plus 11 is 101, because that's what the hardware says. Now you deal with it. All right, so if you move a little away from just from fruits and add things like functions, higher order functions, and data types, and objects, and classes, and modules, and all the features of programming languages, and try to put types over that, well, you get a very interesting formal systems that have been the topic of much study, and in particular by Luca in the 80s and 90s. So that can go in several directions, towards mathematical semantics, towards logics and connections with proof theory, towards process calculi, or towards more applied things like security, types for static analysis, types for compilation. But I think one of the applications that Luca was particularly keen on is type systems for language design. And the idea that the type systems gives structure and strength to language designs the way a skeleton gives structure and strength to many animals. And if your language doesn't have a solid notion of types to begin with, then basically it is spineless. Okay, it looks like jellyfish, and case in point, JavaScript. All right, and so as already mentioned by Dave and Gordon, so Luca did a lot of work on language design, so big languages and smaller languages. So probably the bigger is Modula 3, the object-oriented part that he designed. But I'm particularly fond of his smaller languages. So Ember, Quest, and Oblique are the 3 I know best, but there are others. Because they are clean slate designs, starting with a few orthogonal ideas and carrying them to completion, and then coming with meticulous implementations. And likewise, when it comes to publications, so of course, Luca published a lot of impeccable conference papers. So he described this activity to me one day as engineering inference rules. But I'm particularly fond of his slightly less academic writing, like this survey with Wegner and this chapter in a handbook, or the Typeful Programming report, which is both, well, lecture notes and Quest user manual. And well, that's his manifestos. Okay, he really explains why he cares about type systems and why we should. All right, so moving to well, let me go back to one of these texts, one about polymorphism and type abstraction. So basically, well, we think now that we understand them well and as kind of dual concepts. So polymorphism is just universally quantified type variables. If you have a function that reverses a list, and for all type t's, it's going to take a list of t and give you back a list of t. So I think this is pretty well understood today, and it's even standard in mainstream languages like Java or C#. Type abstraction, well, of course, it's existentially quantified type variable. So there exists a type t, but you don't really say which one exactly, that comes with some constants and operations, for instance, to have finite sets of integers. And why is this interesting, this abstraction? Well, typically to enforce invariance over data structures, maybe your integer sets will be represented as binary balanced search tree. So not just any binary tree, but one that is a search tree, not that one, and one that is balanced, not this one. And so if the operations over your abstract type enforce this invariance, then they will hold for the whole program execution. Then there are notions of representation independence. Since the rest of the program doesn't know about the implementation of the abstract type, you can change it, preserving functionality, and the rest of the program will not know this. And there might be some uses for information hiding in language-based security. You see a little bit of that in the security infrastructure for Java and C#. But, well, I think the security people believe that it's not quite enough and needs to be complemented with more classical approaches like cryptography or hardware-based protections. All right. And then so far so good, but then a problem that was identified early is that how does it work for a big program where, for instance, you have two pieces of code that want to exchange values of type integer sets, okay? Knowing that they are linked with one of several possible implementations of this integer set abstract type. And it's actually quite hard to make sure that the two clients use the same integer set implementation, or at least compatible ones. And for that, basically, you need to give an identity to the various types T, which are existentially quantified in all three implementations. Okay, and there's really no consensus on how to doing that. Okay, so this is a partial landscape. At one end, there's the idea of using global unique names, like include or modular, but that's a very static view of the world. Doesn't support things like runtime generation of abstractions. At the other hand, there's beautiful formalization by Gordon Plotkin and John Mitchell based on packages, which is completely dynamic. Packages are first-class values, but has absolutely no notion of identity. In the middle, you have standard ML functors that are also based on names, but not as syntactic as those ones, and support a little bit of runtime generation of abstraction through functors. And then a lot of work that tried to either take SML and extend it towards richer, more dynamic handling of abstractions like higher order functors, applicative functors, first-class modules, or going the other way, starting from here and adding some other typing machinery to make it more like SML, basically. And so some of that work gave rise to Moscow ML, for instance, and OCaml too. But then there are also plenty of other approaches, completely different, like based on mixins and virtual classes in Scala, and probably others that I don't know about. So it's a little bit of a mess. And actually, the internship I did with Luca, memorable internship I did with Luca in '89, was basically starting from here and doing a baby step toward there. And then in the 90s, I kept working on that in the context of OCaml and eventually moved on to other research topics. And recently, I'm coming back to it for kind of a different angle. So for the last 10 years, I've been using an interactive interactive theorem prover, so the Coq proof assistant, well, to do specification and proofs of programs, like things like bytecode verifiers, compilers, static analyzers, etc. And I'm now using Coq also as a programming language, because in the specification language, there's a pure terminating functional language that comes with super rich dependent types. Okay, so in the type system of this language, you have the full power of logic. And it's interesting to look at how the Coq standard library defines data type with invariance, like finite sets. So that's the work of Letouzet and Filiat. Well, they start with some very concrete representation of binary trees and then define operations, just like you would do in ML or Haskell. And they define the invariant that values of type hyper should respect. For instance, that it is a binary search tree. So that's just a logical statement, a logical proposition. And then they prove the concrete operation under well-formed-ness hypothesis. So well-formed-ness is preserved by operations like row add. And if the argument is well-formed, then you have the expected algebraic equality over add and mem. All right? So far, So good. And the next step is to encapsulate all that in a dependent type. So the type of finite sets is actually a dependent pair of a data S of type hyper and a proof term that proves that it satisfies well-formed of S. Okay? And then the concrete operation, the row operations, can be wrapped so that they propagate the invariant. And so you get add, which is a function from T to T. And you can specify and prove the wrapped operations without well-formedness hypothesis because values of type T are kind of self-certified. Okay? They carry their own proof that they are well-formed. So it's pretty nice, and you will notice that we are not using any kind of type abstraction here. The type T is completely concrete and structural. And that gives a bonus point, which I found useful recently, which is extensibility a posteriori. It is possible for client code to add new operations over sets that need access to the representation, a bit in the style of O inheritance. For instance, I had the need for operations like, given a set, tell me if it contains an element between 2 and 25. Or given a set, give me the subset of all elements between 2 and 25. And if you have access to the binary search tree representation, then there are very efficient algorithms that do this, okay, just by cutting branches that are clearly below or clearly above. But if you don't have access to this concrete representation, you don't get the good complexity. All right. So to summarize, in this approach, there's no abstraction to speak of, but no syntactic type abstraction at least, but it's very good at enforcing data structures invariant. It even proves them, okay? And the invariant can be quite complex, talk about the current state of the data, but also about kind of the history that led to its creation. There's no representation independence to speak of because the client code can depend on the concrete representation, but at least if you change this concrete representation, or you change the invariant that holds over it, the client code will not type check or will not proof check. So at least you get error detection. There's a priori no information hiding, but you get extensibility a posteriori, which might be useful sometimes. So to conclude, how abstract should an abstract type be? Well, I still don't know, but at least I and all of us can look at the question maybe from new angles, coming from, for instance, dependently typed languages like Agda and Coq. And at any rate, I'm grateful to Luca for introducing me to that question a long time ago. So thank you.